Morning, guys. Today we're going to do double angles identity, and in part 2 we're going to do our power and our half angle. So right now let's concentrate on our double. So you can use the sum identities and the Pythagorean identities to derive these double angles. If you want to see the proofs, you just have to look in the book. But right now we're just going to do some examples on the use of these double identities. As you can see, cosine has 3 different ones that we can choose from, and you can choose from either one of these guys. So depending on what's given to you is the best way to go. Let's look at example number 1. Suppose our point is -3, 4, lies on the terminal side of theta when theta is plotted in standard position. So let's make our xy axis. We go -3, 4. Okay, so this would be theta, -3 and 4. Now, of course, as you can see in our identities here, we need sine and cosine. Cosine is x over r. Sine is y over x, or y over r. So we need our r to begin. So let's find that now. Remember that r equals the square root of x squared plus y squared. So when we do those calculations out, we get r equals 5. So let's write down what that gives us. That means that cosine of theta will be x over r, and sine theta is y over r. There we go. Okay, our next thing in our problem here is to find cosine double theta and sine theta. So cosine. Again, we can use either one of these, but I'm going to stick with, since we have sine and cosine, I'm going to stick with the first identity for cosine double theta as our cosine squared, so -3/5 squared, minus our sine squared, which is 4 over 5 squared. All right, that gives us that we have 9 over 5 minus 16 over 55. Oh, 25. There we go. Sorry, guys. Forgot to square the whole thing. All right, so when we subtract these two together, we get -7 over 25. So cosine double theta is -7 over 25. Let's try sine. Sine double theta equals 2 times sine, so 4 over 5, times cosine, -3 over 5. Multiply straight across, that's -24 over 25. Okay, let's finish the problem because there's more that we have to look at. It says determine the quadrant in which the terminal side of the angle double theta lies when it's plotted in standard position. So since both come out negative, that means that double theta lies in the third quadrant, quadrant 3. So we have to look at our result to make that conclusion about where double theta would lie. All right, so let's check this one. If sine of theta equals x for -pi/2, theta is in between -pi/2 and pi/2. So that is the first and third quadrant. Find the expression for sine double theta in terms of x. Okay, so what we need is sine double theta. So we're going to go back up to our identities here. And we have sine of theta is x. We need to find cosine of theta first. So I'm going to say find, so we can look back at our notes. Find cosine theta. All right, we can do this by the Pythagorean identity, right? If we have sine, we can find cosine. So I get sine theta plus cosine squared theta equals 1. Now, yes, guys, there's a variable in here, so we are not going to come out with a numerical number there, or numerical value. I mean, we're going to come up with an expression with x in it. So let's solve for cosine. Get 1 minus x squared, square root. So cosine, not squared, we're square rooting it. And while I'm erasing this, let's keep this in mind. Remember, we're in the first and fourth quadrant there. So what is cosine in the first and fourth quadrant? It is positive. So even though that this could be two values, it is a positive value since theta is in between the negative pi over 2 and pi over 2. Okay, so now we have cosine, we have sine. Now we can find our sine double theta. So sine double theta equals 2 times our sine of theta, which is x, times our cosine of theta, which is our square root of 1 minus x squared. And what do you know? We don't have to do any more manipulations, so we can keep that as our answer. All right, last example, but we have part A and part B. You can also verify identities using double identity angles. So what we're going to do is do some proof. Remember, we manipulate one side to make it look like the other. And remember, it's easier to condense something that's big than to expand something that's small. So as you can see in A right here, I'm actually going to look and manipulate the right side there. All right, so the first thing I see here is I can use the Pythagorean identity. And I'm going to write down my steps so that way you guys know what we did. So secant squared theta, and that's the Pythagorean identity. Then what we're going to do, as you can see, I have a tangent in there, and it's easier to see tangent as sine cosine, and it's easier to see secant as 1 over cosine, because maybe there's somewhere that we can change. So I'm going to change this. I'm going to look at this, separate it first so you guys can see what I'm doing, as 2 tangent times 1 over secant squared. And now I'm going to change tangent to sine over cosine. And I'm going to change 1 over secant, which is cosine, but we know it's squared, so cosine squared. Now, if you look, one of these cancels. So I'm left with 2 sine theta times cosine theta. And what do you know? This is the double angle for sine. So we get sine 2 theta. And that's what we wanted. So this is reciprocal and tangent. Simplify. I'm just trying to do those steps, guys, so that way you can see where I'm going at. Okay, now, of course, that was A. So I'm going to come down here and do B so I can leave some of those steps. Okay, so let me write B down here. So we got tangent double theta, or 2 theta, equals 2 over cotangent minus tangent. Looks a little bit more complicated, but let's see. All right, so one thing I don't like is I don't like the cotangent tangent stuff right here because it's hard to see what can cancel and what can't. So actually, I like working, and this is the way to go, with sine and cosine. So let's actually do the tangent and cosine identities with sine and cosine. So I'm going to manipulate that to 2 over cotangent is cosine theta over sine theta minus sine theta over cosine theta. All right. So this is cotangent tangent. Okay. Now I have 2 fractions in the denominator, but I'm going to focus on that I have 2 fractions. I want to make it 1. So I need common denominator since it's subtraction. Okay. This will make, I need this fraction multiplied by cosine over cosine. So I get cosine squared minus, now multiply this fraction by sine over sine. So sine squared theta. Now, of course, that's still all over our common denominator of sine theta cosine theta. So this is common denominator. All right. Well, of course, when we divide by a fraction, it's the same thing as multiplying by its reciprocal. So what happens is we get sine, or 2 sine theta cosine theta all over cosine squared theta minus sine squared theta. So multiply, leaving myself alone, not multiply by reciprocal. All right, next. Very careful. Many of you make this mistake right here. You cannot simplify and cross those out because of the subtraction. If it was all multiplication, we could do that, but we can't. So now we're going to use a double angle theorem here because cosine squared minus sine squared, okay? If this were plus, this would be the Pythagorean identity. But because it's subtraction, if you go back on the other page to your cosine identities, you would see that that is a double cosine. So 2 sine theta cosine theta all over 2, not 2. I need an eraser. Cosine 2 theta. There's my 2. But wait, I see another one in there, right? Do you guys see it on top? Because 2 sine cosine theta is sine double theta. Sine 2 theta. Awesome. So this is our double angle identities. And what do you know, guys? What is sine over cosine? Sine over cosine is tangent. And then, of course, we are in 2 theta. And there is our tangent. Awesome.